Hello, dear fellow machine learning enthusiasts. We are Group 9, Sharun and Sreerag, both from School of Physical Science, National Institute of Science Education Research. And today, in this video, we are going to discuss feature engineering. In simple words, what ML does is take some form of input data and give us the output by learning from the statistics of the given data. The input data comprises of features. The data we give to the machine is crucial for better output. Just go through a cartoon.
This is your machine learning system.
Yep, you put the data into this big pile of linear algebra, then collect the answers on the other side.
What if the answers are wrong?
Just stir the pile until they start looking right. This is the feature engineering. The data we give to the machine is crucial for the better outputs, as I said before. Once Luca Masaran, author of many books on data science and machine learning, has said, features you use influence more than everything else the result. No algorithm alone, to my knowledge, can supplement the information gain given by correct feature engineering. His quotes are very significant, and yeah, feature engineering is very important for better results. This is results from Forbes survey. As you can see, most of this time is spent on preparation on the data, like collecting data, building training set, cleaning and organizing data, and so on. So what is exactly feature engineering? The main goal of feature engineering is to prepare a proper input data set for machine learning algorithm that we are using and improve the performance by choosing the aptest data. So I hope everybody have a rough idea what feature engineering is or the implications of feature engineering. There are several techniques used in feature engineering, and we'll be discussing these techniques we'll be discussing in this video. Imputation, handling outlier, binning, log transform, one-hot encoding, grouping operations, feature split, scaling. This video is divided into two parts. First four techniques and the other last four. The last four will be discussed by Sreerag. And we will start with imputation. Imputing. So as you can see from this picture, this kit is trying to fill the void. That's what imputing is. One of the major problems that people face in missing values. This can be due to inherited property of the data, or maybe due to human error, privacy concerns, or so on. But either way, the missing values are problematic. Depending on the algorithm, it either reduces the amount of data by dropping the rows uh, or give us an error. Majority of the time, there'll be error. Imputation is the process in which we replace missing values with a numeric value or a category. There is no exact way of imputing. It depends on the data, but most of the time we can replace missing data with median without changing the statistics much because median is the most repeated data. So if you repeat it more, then the statistics won't change much. But if you change it with mean, the statistics is probably going to change. And this will be only possible for numerical data. And in case if you are merging two tables of different sizes, replacing missing values with zeros seems to be a good option. So this is the code for uh, replacing the missing values with 0. This fill NA is the voids, which will find the voids and replace it with this value 0. This is a function from package pandas, and here this is the one we are replacing the missing values with the uh, median, and this one is for the categorical uh, data. Next, we'll go to outlier handling. So outliers is an issue because outliers can make the data like it's going to give the machine learning algorithm a tough time because they are like noise in the data. So as you can see from the visualizing, like if you visualize the data, it's much easier. Like outlier can be easily detected, just like this fish in red. The most efficient method is to identify outliers by visualizing the data. But if the data is too complicated, like in higher dimensions, like 5 or 4 dimensions, it's very difficult to uh, do the visualization. Or is it maybe it's impossible? In those cases, we can use statistical methods like using a threshold standard deviation, percentile, or capping. Capping is the maximum and minimum values replacing values and replacing them with an arbitrary value or a value from a variable distribution. Capping instead of roping might give you better performance because the data science remain the same, but we cannot guarantee the performance because it can even alter the statistics so that the output will be not as desired. So this is an example code which we have set a threshold for the standard deviation. If this data is above, like if it's deviating 3 times the standard deviation, then it's not being considered. So this is the code for that. It will be in like upper limit and lower limit is been specified. So that data from the top part and the bottom part will be cut off. Next is binning. Binning is exactly as it sounds. It's a way of grouping. It can be used in both numerical as well as in categorical data. The main motivation of grouping is to find a sweet spot between overfitting and loss of information. As you can see from this graph, the binning is too much, so some data is lost. But here, it causes an overfit, and this one is the sweet spot, as I said. This is an example of binning. So in numerical data, we have a range and we give it to a bin. For categorical binning, we take each categories and make it to a bin. It's fairly easily done with Python. You can use pandas. The next one is log transform. As the name suggests, it's simply taking the log of values. It can be only applied to non-negative numbers because it's log. There is no defined log for negative values. And yeah, it can be only used in numerical, it's obvious. So when is this particularly useful? This example is exponential decay. So here, when we transform it, it's a straight line, which is more easy to interpret. This one is a curve, it's an exponential curve, but this one is a straight line, so much easier to interpret. So another example is the changes concerning age. So why is it that? So the changes are much faster in younger ages, and it gets slowed down as we grow older. In such cases, Log transform will normalize that effect. With the same mechanism, it also reduces the outliers. This is a code in which which we are uh, illustrating the log transform. It's fairly easy. So adding a one, if you have noticed it, that's because if you have a data less than one and greater than zero, the log will be negative. So we can just shift it with one and we'll get non-negative data, which is good to interpret. And here I left to Sreerag. So stage is yours, Sreerag.
The next feature engineering technique which we are going to discuss is one hot encoding. One hot encoding is one of the most common encoding methods in machine learning. We know that in machine learning, we are dealing with computers, and computers can only understand numbers. Let's say we are having some categorical data as input data set. Then for making our computers to understand it, we must convert this categorical data into numbers. Let us understand it by considering an example data set. Let's consider this table. Here in this table, the column city actually represents a categorical variable, and it is difficult to be used in machine learning. So what we can do is we can convert this city column into more like a numerical or integer number. And one of the technique, there are several techniques, and one of the most common technique is one hot encoding. For this, we can use pandas. In pandas, there is get dummies function. If you give this column as input to those get dummies function, it will return the table which is converted into numerical values. So our data will be after giving into get dummies function. Our data will be finally look like this second table. Uh, what it has done is that it has made every single city name into one of the column by itself with binary values, which can be easily understood by machine learning algorithms. The next machine learning feature engineering technique which we are going to discuss is grouping operations. In most of the machine learning algorithms, every instance is represented by a row in the training data set, where every column show a different feature of the instance. This kind of data is commonly known as tidy data. Uh, Here we can refer to Hartley William, who is an famous author of many books on statistics and data science, has said about tidy data like this. Tidy data sets are easy to manipulate, model, and visualize, and have a specific feature. Each variable is a column, each observation is a row, and each type of observational unit is a table. Uh, but in reality, let's look into what happens in reality. In many cases, our training data set may not fit into this tidy data type definition. For example, data sets such as we are commonly seen in transactions, they commonly rarely fit into these tidy data definitions because uh, we commonly observe multiple rows for a single instance. In such cases, what we can do is that we will group the data by instances, and then every instances will be represented by one and only row. uh, so this is let's understand it by consider an example. Here we can see for each users there are several rows in the table. So for making the machine to understand it easily, we will group each user, the several instances of each user into a single row, and which is done by grouping. The main group of this grouping is to determine the aggregation function of the features. For that purpose, sum and average are functions are usually convenient for numerical data. Here it is a sample code of implementing a grouping on a sample data set. Here we used sum and mean functions to determine aggregate value of a group corresponding to a feature. Yeah, here you can see this. Here we use sum and mean function to determine aggregate value of a group corresponding to a feature, and then concatenated or joined each of these groups to form two rows of the new data set. That's the final step of this code. So usually it is simple in case of numerical data. So as you are seeing in this example, whereas when it comes to categorical data, it is a bit complicated. The next feature engineering technique, which we are going to discuss, is feature split. It is very good way to make our data useful for machine learning algorithms. Most of the time, our data set might be having string columns, which violates the tidy data principles. By extracting the utilizable parts of a column into new features, we enable machine learning algorithms to comprehend them and allow them to categorize or group the data. And also by exposing a potential information, by this way, we can improve the model's performance. Because of these advantages, splitting features is a smart choice in many cases in machine learning. But there is no one size fits all solution for this. Then how we splits our data? We splits our data or a particular column, and the criteria for that is basically determine that particular column's attributes. To understand this, let's start by discussing a couple of examples. In this example code, we are using split function of pandas package. Here, firstly, we inputted a regular column of names here in this first step. Then from the name column, firstly, we separated only the first part of the names and then extracted only the last part of the names. Here in the second part, we separated the name in accordance with where the space occurs, and from that separated parts, we separated the first part and last part. and that first part and last part are extracted using map function from that separated list. Uh, to extract a string segment between two characters also, this split method is useful. And this is a sample code for that. Now let us discuss about scaling procedure in feature engineering. Let us start by discussing what it's need in machine learning. The numerical properties of the dataset in most circumstances do not have a fixed range and differ from one another. For example, if we consider age and income columns in a dataset, we can expect these columns to have same range, and if we expect so, that is really absurd. Then how these different columns of completely different natures can be compared from the standpoint of machine learning. This issue is basically solved by scaling. After scaling process, what happens to the dataset is that the continuous features become similar in terms of range. Um Although this step is not compulsory for many machine learning algorithms, it's always a good idea to do so. Whereas for distance-based algorithms like and k-means, it requires scaled continuous features as the input for for their models. So it's compulsory to scale the data set in in these algorithms. Now, in what ways we can do this scaling procedure in our data set? Most common procedure followed for scaling are normalization and standard deviation. And now let us look into the first procedure, which is normalization. In normalization, all values of the column which we are normalizing is basically gets scaled into specific range between 0 and 1. This modification in the dataset is not going to influence the features, and thereby it preserves the basic nature of our dataset. Uh, this is the basic expression for the normalization procedure, as the value of x minus x min is always less than or equal to x max minus x min. The maximum value possible for any normalized data point is 1. So for x norm here, we will be getting 1 as the maximum value, and its graphical representation of what happens to the data set before and after the normalization is represented here. And the main disadvantage of this normalization procedure in our data set is that it increases the effect of outliers. And it is evident in this graphical representation. Uh, and this represents the data set before the normalization procedure. And here you can see the outliers does not have a significant effect on our overall data. And after the normalization procedure, and if you look into where the outlier stands in the data set, it has increased effect on the overall data set. So outliers are basically noises in our data set. So the noisy data gets amplified in the data set, in the normalized data set. So it is always recommended to deal with the outliers before we are applying normalization procedure in our data set. Here it is a sample code of implementing normalization on a sample data set. In the first line, we defined sample data set in pandas data frame. Here, in this line of code, and then we produced data frame containing normalized data by applying normalization equation of the data points, which represents this line of code. Here, this data value minus data value min divided by data value max minus data value min is basically this equation. So here ask the output for the data points in the normalized data matrix. We will be getting the normalized data of the input data points. And here it represents the data points before and after the normalization procedure. Now let us discuss about the next most common scaling procedure, which is standardization. Standardization, which is also known as set score normalization, is the process of scaling values of a particular column of a data set while accounting for standard deviation. So, as we are accounting for standard deviation here, the range of a feature will also differ in accordance with the difference in the standard deviation of the data points. And as a result, in contrast to normalization procedure, in this standardization procedure, the effect of the outliers in the characteristics of the data set also get reduced. This is the basic equation for standardizing a data point, where x basically represents the data point which is standardizing, and mu basically represents the mean value of the data column, and sigma represents the standard deviation. And here z is the standardized data value of the data point x. And here it is a graphical representation of what happens before and after the standardization procedure on the data set. Here it is a sample code for implementing standardization in a sample data set. In the first step, like we have done for normalization procedure, we defined a sample data set in pandas data frame, which is this line of code. And then we defined a data frame of standardized data point by applying standardization equation on the data points. So after this is the output of this code, which represents what happens to the data points before and after the standardization procedure. These are some of the feature engineering techniques, and each one of them has its own unique advantages. And it should be used in accordance with the data sets as combinations or otherwise. There are other techniques which have been discussed in this lecture video, and it's all boils down to your data set, and the aim of it is to make or transform the data so that machine learning algorithms can give us the best possible output out of our input data set. And these are the references which we have referred for making this lecture video. And thank you.